All right, hey folks. Last video lecture for chapter 8. So this should be a pretty short and sweet one. So I'm going to talk about these last three learning goals. So understand the trend of bond energy and bond length. Okay, so we're going to talk about that. So know how to calculate enthalpy of a reaction. So this is going to be a new way of calculating things using delta H, but it's very similar to what we've done before. Okay. And then last, just a very, conceptual kind of for your own information, be familiar with why certain compounds are greenhouse gases. As it turns out, it has to do with the type of chemical bonds they have. Okay. And so we'll talk about that as well, and then we'll finish off this chapter 8. All right, let's get rid of that. Okay, so the first order of business, lengths and strengths of covalent bonds. So I showed a figure like this before when we talked about electrostatic potential energy, okay? And we talked about this with respect to ionic bonding, but it's still the same situation with covalent bonding, okay? When you're very far away, like you can see these two, let's just say two nuclei. We won't even say that they have to be ions. They could be. They could be a negative and positive ion. But it could also just be two carbon atoms, carbon and carbon, okay? When they're very far away from each other, so note on this x-axis, right, it's distance between the two nuclei, right? So this distance between the two. And on the left, it's the potential energy. And recall, in thermodynamics, we set the scale that, when there's zero, arbitrarily selected, zero potential energy, we say those two ions are not interacting with each other. Or in this case, these two carbon-carbon atoms. They're far enough away that they have zero potential energy between the two. But as they get closer and closer, this potential energy goes negative, and we reference that as negative to be beneficial. There's a benefit of these two nuclei coming together and sharing electrons, okay? And they get to this spot right here. We call that, well, I like to call that the sweet spot. Really, that sweet spot gives us the bond length and bond energy, okay? So you can see right there for a, so this is not connected to the data that I have right here, okay? But whatever this, whatever these two nuclei are, right, we would say then that they have a bond distance, a bond length of 74 picometers, okay, right there. And we would also say they have a bond energy of 432 kilojoules per mole. So we just use the absolute value. Again, we view this as negative as just a reference point, okay? So now here are some realistic bonds with their energies and lengths, okay? So a carbon-carbon single bond, carbon-carbon double bond, and a carbon-carbon triple bond. And what you can see, hopefully maybe you expected this, you can see the energy goes up, which is not all that surprising, right? A double bond should be stronger than a single bond, and a triple bond should be stronger than a double bond. And we see that with the bond energy, okay? And also, maybe you expected this, maybe you didn't, but the bond length, as you can see, as the bond energy gets bigger, the bond length gets shorter, okay? So that carbon-carbon triple bond, really pulls those two nuclei in together, down to 120 picometer, much shorter than the 154 picometer for a carbon-carbon single bond. And so what this means is this is a fairly rigid bond, okay? It's really hard to stretch and elongate. We call this vibration. It's much more difficult to vibrate that carbon-carbon triple bond than it is that carbon-carbon single bond, okay? And as a result, that can change the chemistry, okay? Okay, so let's move forward. So there's another way we can think of calculating the delta H of a reaction. Remember, don't forget about enthalpy. Just because we're on a different chapter doesn't mean enthalpy goes away. And this way of calculating delta H is still, I'm going to write over here, it's still H final minus H initial, okay? But the way this ends up working, because of the fact that we have to supply energy to break bonds and that we get energy out when we form bonds, okay, this formula ends up becoming bonds broken minus bonds formed. Okay, so it's a pretty easy to remember. The sum, so right, sigma, that tells me the sum with all the number of moles times the energy of the bonds broken minus the sum of all of the energies of bonds formed. Okay, and as an example, here you can see this is the reaction, the combustion of methane. So let's write that down. Combustion of methane. All right. And we can see overall here when we start, this is my initial state right here. And this is my final state. And we can see it's exothermic as expected because it is a combustion reaction. However, we can start to see now why you have to spark a mixture, right? When you have a mixture of methane and oxygen, it doesn't necessarily spontaneously combust, though it could if we raised the temperature high enough. That's called the flash point. So we do have to put some energy in to get those bonds to start to break, right? Specifically, we have to break 4 carbon-hydrogen bonds and 2 oxygen-oxygen double bonds. And that gives us all of our available atoms, okay? As it turns out, the chemistry is a little bit more complex than that, but all the same. Now when all of these bonds are formed, specifically 2 carbon-oxygen bonds and 4 oxygen-hydrogen bonds, that releases a ton of energy. And if we compare the energy in to the energy out, you can see overall, right, that gives us our delta H, our negative 808 kilojoule per mole. Okay, so let's go, I'm going to actually walk you through that, and let's do that as a sample calculation. Okay, so we're going to do the combustion of methane. Okay, so first let's get that reaction. CH4 plus O2 makes CO2 plus H2O. Additionally, when we do this way of calculating delta H, we have to get the right Lewis structures. Okay, so let's do that. We know that methane is all single bonds, and obviously, you know, I had it on the other page, right? But and then I didn't balance the reaction, did I? Okay, so 1 carbon and 1 carbon. Let's see, 4 hydrogens. Aha, I have to put a 2 right here to make 4 hydrogens. And then now I've got 4 oxygens, so I need a 2 right here to balance it. Okay. So as I was saying on that other slide, you saw all the Lewis structures. But you know, in a homework problem or in another calculation, you would first have to get the Lewis structures. So you get the balanced reaction, then get the Lewis structures. Okay. So hopefully you remember that oxygen has a double bond, okay, with 2 lone pairs on each oxygen. And of course, there's 2 of them, so I'm going to draw both of those oxygen molecules so I don't miscount my number of bonds. And let's see here, we're only forming 1 mole of CO2, okay, and we remember CO2 looks like this. And we're forming 2 moles of H2O, and oxygen is the central atom there with 2 lone pairs on oxygen, and we made 2 of them. Okay, great. So now we can count up all the number of bonds, and we can get the formula. Okay, we can get the calculation going. So delta H of reaction is, let's remind ourselves, bonds broken minus bonds formed. Okay, so my bonds broken, I'm going to have 4 carbon-hydrogen bonds, right? 1, 2, 3, 4. Okay, so let's do that. So we'll say 4 and then times, let's see, where is it? Here we go. CH it's 110 picometers and it's 413 kilojoules per mole. Okay, and so let me write down, let me put the unit in front of that 4 so we recognized, so 4 mole, right? The mole and the mole is going to cancel, okay? And now that's plus 2 oxygen-oxygen double bonds. So this is why we have to get the right Lewis structure, because here you can see on this chart I've got an oxygen-oxygen single bond, but we really need the oxygen-oxygen double bond. So that's at 495. So I did it again. 2 moles. 2 moles times 495 kilojoules per mole. So that's the sum of my bonds broken minus my bonds formed. So there's only 1 carbon dioxide, but there's 2 carbon-oxygen double bonds in the carbon dioxide. Okay. So let's go and look at the list here. Carbon-oxygen. Oh, look, there's a little note next to carbon-oxygen. Aha. The bond energy of a carbon-oxygen bond at CO2 is 799. That's an exception. So make sure you notice that. This table doesn't have any other exceptions, but every now and again, you will see something like that in these tables because chemistry is the science of exceptions. You knew that. Okay, so there's now 2 moles of carbon-oxygen double bonds in CO2 at 799 kilojoules per mole. Okay, and then now that's plus 4 oxygen-hydrogen bonds, right? Each H2O has 2 moles of oxygen-hydrogen bonds, but we have 2 moles of H2O to give me 4 in total. So now an HO bond, there it is, 463 kilojoule per mole. And I just realized I have my periodic table up here, but really for this lecture, I needed my calculator. But if we were to go to do this, you should prove this to yourself. So luckily, the answer was already on the right page. So prove this to yourself that it works, okay? If we were to go through and calculate this whole thing, we would come up with that negative 808 kilojoules. So give that a shot, okay? Great, and so then finally, I think the last thing to discuss, yes, just very briefly, look at that. Only a 15 or so minute lecture. You've probably heard carbon dioxide is a greenhouse gas, so I want to spend some time talking about that. There's other things besides carbon dioxide as greenhouse gases. And as it turns out, it's all about the bonds, okay? So when you have something that has a polar bond, so what makes a greenhouse molecule? Well, it needs to have actually not only just a polar bond, but overall the molecule needs to possess a dipole moment, okay? And the reason for that, I'll show you that in a moment. It's fairly complicated, but it has to do with how the molecule interacts with infrared radiation, okay? So I'm only going to describe the greenhouse effect here very, very briefly. I would encourage you to research more if that's interesting to you or if you're not familiar with it. But as visible light comes down to planet Earth from the sun, a huge amount of visible light, okay? It heats up the surface, and as a result, the surface gives off some of that heat. And it gives off some of that heat in the form of infrared radiation, okay? Just like actually I give off heat in the form of infrared radiation, okay? If we were to turn all of these lights off and you had some really fancy like SpyTech infrared, night vision goggles or whatever, you would see me glowing infrared. Well, as it turns out, planet Earth also glows infrared because it's a fairly warm object in the grand scheme of things. Average planet-wide temperature, 286 Kelvin. And that's in the middle of space where the temperature is 1 Kelvin or so, okay? So Earth gives off infrared radiation. And as it turns out, some molecules are really good at absorbing infrared radiation. The type of molecules that are good at absorbing infrared radiation possess a dipole moment, okay? And so this picture is showing you all of the things that happen to carbon dioxide when it starts to absorb infrared radiation. It makes the bonds vibrate, okay? And so if, let's say, my torso is the carbon and my arms are the oxygens, okay, it can undergo what's called the symmetric stretch, where each oxygen atom compresses and then recoils, and compresses and then recoils. Well, as it turns out, this doesn't give you a dipole moment, okay? Right? Carbon dioxide, if you look at this here, this dipole moment, the way that this thing is lined up, both of these cancel each other. So carbon dioxide does not have a dipole moment at rest. And when it's undergoing this symmetric stretch, it doesn't have a dipole moment either. So that's why it's called infrared inactive. However, if we look at what's called the asymmetric stretch, so this is now where one of these things moves in like this and the other moves like this. Okay, I'm watching myself trying to do this little dance here, right? And I should just pay attention to the screen. So this is called the asymmetric stretch. And as it turns out, there's definitely a dipole moment in that mode, okay? Right? When this oxygen is compressed, the dipole moment is very short on that side. And when this oxygen is elongated, the dipole moment is very long on that side. And that gives it an overall net dipole moment. In fact, it's a really strong overall net dipole moment, okay? There's also another infrared active, so that one's active. There's another infrared active mode, and that's called the bending mode. And that's where these oxygens are actually able to move up slightly like this and down, okay? And as it turns out, that also gives you a dipole moment because now in this configuration, I could draw the dipole moment pointing down this way, and I could draw the dipole moment pointing down this way. And overall now, or of course we could see in this configuration, it looks like this, right? And when it's in this position, there's an overall dipole moment pointing down. And when it's in this position, there's an overall dipole moment pointing up. Okay? Well, how is it that that influences, or how is it that infrared energy can do that? Well, when we look at a wave of light, okay? So here's like a, let's say a couple waves of infrared. And let me draw a little dotted line through the center of that, okay? Well, as we discussed in Chapter 7, light is an oscillating electromagnetic field. We talked about that very briefly, okay? So as light is going through this wave, there is actually a dipole moment created by light itself, okay? And so that's why I wanted to draw that dotted line right there, because you can see at each crest and trough, the dipole moment increases. And if we were to align a carbon dioxide molecule in this dipole moment, okay, like let's say I'll put one right here. So here's my carbon, and I'm just going to draw it, without the correct Lewis structure. I'll just draw it like that, okay? So now as this wave propagates through, this influences that bond to stretch. And then as it comes back down, it's going to influence it to compress the other way back until you get a full cycle. Hopefully you can kind of see that, right? So as that wave is propagating through the CO2, it's influencing it to go through those motions, okay? And what the carbon dioxide can do is absorb that excess energy. So it stores that energy in the form of these vibrations, okay? So the way that these molecules are vibrating is a way of storing that energy. And because normally that infrared energy would go back out to space if there were no greenhouse gases, then that leaves the planet warmer because those molecules are storing that excess energy that normally would make it back out to space. Okay? So as it turns out, CO2 is an excellent greenhouse gas molecule. And in fact, we should be lucky to have a little bit of a greenhouse effect because the planet would be way too cold. Okay? Without the greenhouse effect, the average planet-wide temperature would be roughly 250 Kelvin. With the greenhouse effect, the average planet-wide temperature is roughly 280 Kelvin. And so we're talking about the average planet-wide temperature. Okay? So 250 Kelvin as an average planet-wide temperature would mean that we'd be a ball of ice, right? Water melts at 273 Kelvin. We would be an ice planet if we didn't have some amount of greenhouse effect. Okay, so we do want some, but right now we have too much. We're overwhelming our planet's ability to deal with that excess heat. Okay, so CO2, because it's polar, or it can induce a dipole moment from infrared energy, is a good greenhouse gas, excuse me. As it turns out, H2O is a really good greenhouse gas molecule. It has a bent geometry, and we didn't talk about this so much when we did the Lewis structure. I just kind of drew it flat. When we get into the next chapter, we'll see that water is actually bent. And so that means that it has a dipole moment at any configuration. So water is a great greenhouse gas. Another one, which maybe is kind of surprising because at first it looks symmetrical, methane is an excellent greenhouse gas. In fact, methane, mole for mole, is a much better greenhouse gas than is carbon dioxide. And when you look at this, you might think, well, methane at rest has no dipole moment, but it can undergo these asymmetric vibrations, okay, which allow it to interact and absorb infrared energy. And in fact, it's a much better greenhouse gas because for a given atom, right, carbon has 2 bonds, but carbon dioxide has 2 bonds, but methane has 4. That's 4 bonds that can store infrared energy in the form of these molecular vibrations. Okay? So, in fact, if we were to release a lot more methane, that would be devastating for the planet. So there's a lot of people that are pushing for more combustion of methane, which of course we know when you combust methane, it releases CO2, right? But any uncombusted methane, if you don't do complete combustion on that, that's also going to contribute to the greenhouse effect. So in general, we should not be burning fossil fuels at the rate that we are. That's the moral of the story. Even if someone tells you, oh, but methane is far more efficient. It is, but it's still a greenhouse gas, okay? And then really even the same with biofuel, okay? When you burn biodiesel, you're still burning hydrocarbon. You're still putting CO2 into the air, and you're still putting uncombusted fuel into the air, okay? So that's really why we should just be moving away from fossil fuels completely. Whether it be methane or octane or coal, we should really just move away from them completely because of what's happening with this greenhouse effect. So I know I only described that very, very briefly. I would encourage you to read more, maybe watch more videos, read more in the book. There's obviously a ton of information out there, but I just wanted to touch on the basics of where the greenhouse effect starts. And it's all about the chemical bonds, which is pretty cool. Okay, folks, that's it for Chapter 8. So our Exam 3 covers 7 and 8. I will start recording lectures for Chapter 9 soon. So keep on top of that. And I will see you all at discussion on Tuesday. All right.